Well, thank you, Peter, for agreeing to join me for this interview. It's a great pleasure for me to be able to interview my former PhD supervisor, Professor Peter Whittle, formerly the Churchill Professor of Mathematics for Operational Research here in the University of Cambridge. So, Peter, let me start off by asking you some questions about your family background, where you were born and when you were born and early family life.
Well, yes, I was born in Wellington, New Zealand, 1927. We lived on, New Zealand has got the two islands, and I was living at the southern tip of the top northern island, looking out onto the straits. So it was really very dramatic and very beautiful, which most of New Zealand is.
How many siblings did you have?
Oh, I had two sisters, Gloria and Gillian. So there were just the three of us. And
you went to school in Wellington?
Yes, I went to school in Wellington. First, I went to the local school. I lived in Island Bay, which is a suburb of Wellington, looking onto the straits. Yes, I went to the Island Bay School first. I was a very mild character, but somehow I had to look after myself. So I bloodied 3 or 4 noses, I'm afraid. It wasn't a nice thing to do, but I remember the teacher saying to me, Peter Whittle, you're too keen with, you're too good with your fists. And then she sort of smiled.
And so which subjects interested you while you were at school?
Oh, the ones I certainly disliked were geography and history, because they just seemed to be masses of data, nothing else. Languages I couldn't understand, well, even English straight away, but later, foreign languages, I always liked getting into a foreign language. And science, of course, and if you once go into science, you get into mathematics. So you sort of do that at one remove. But arithmetic I didn't care for, but mathematics, yes.
Right. And so then you went to college?
Yes, Wellington Boys College. That was a good college, I enjoyed it. I was winning, I may say, prizes by that time, classroom prizes, book prizes, etc. But also the competition, there was the scholarship examination. In other words, one was competing for scholarships. And so one was ranked on these. And I was lucky to be ranked sometimes at the top, but always near the top. So it worked out very well. And the same thing happened when we went to university. One competed for in a scholarship examination, the scholarship being in for postgraduate work. So you were trying to finance yourself ahead of time.
Right.
Yes.
Right. So, and at university as an undergraduate, your main subjects were mathematics, physics and chemistry? Or?
Well, mathematics, physics, and, well, actually I didn't do languages. I say I like languages very much at college, but by the time I got to university it was just science. But I was in town going to the French Society, etc., etc. I wanted to keep that up. And later, of course, I went to Sweden, so I liked that. And even English I liked as a subject.
Right.
But geography and history, no. But languages, mathematics and physics, yes.
So this was shortly after the end of the Second World War?
Yes,
and,
that's correct.
So presumably operations research had begun as a discipline, but was not perhaps widely known.
No, it wasn't widely known. Actually, as I said, I was at the university, but I started working in the holidays while still at the university, and that was NZ DSIR, New Zealand Department of Scientific and Industrial Research. And really that was very helpful to get onto that. That was enjoyable.
And so the problems were natural operational research problems?
Yeah, so, well, it was more, well, optimization in the sense that they were concerned with many things. They were concerned with business, concerned with farming, in several directions.
So the early influences on your work were then partly that work you did with the New Zealand Government Department then?
Yes, certainly, certainly. The interesting thing was the gadgets they had there. Before I went, the group I was in was, first of all, it's called the biometric division, and that gradually became the Applied Mathematics Laboratory, which was concerned more generally. And then the place where we worked during the war had been occupied by the military, and all kinds of gear left lying around, which was very interesting. For example, we had a direct current supply, a DC supply, and I was interested in wanting to do some electroplating, and the solution I used was potassium cyanide, which is a remarkable thing. I had to go down to the chemist and ask for half a pound of potassium cyanide, and a great discussion and shock about this, but somehow I managed to get it in the end, and I got this potassium cyanide, and it worked very well. It did the plating, and but somebody went and tipped all my cyanide away, so that was that.
Goodness, that sounds dangerous.
Yes. There were other things there. One of them was a remarkable piece of equipment. It was Hartrey's original differential analyzer we had. This is thing for essentially solving nonlinear problems. I'd say, as it was made of Meccano with 6 purpose-built rolling ball integrators, and it was actually solving nonlinear differential equations. So that was very interesting. The semi-dismantled analyzer looked like what it was, a hybrid of a giant Meccano set and some special purpose components requiring a lot of insight to bring it into life.
Yes, so Hartrey's equipment there was an analog computer around the time that digital computers were just beginning to be constructed elsewhere.
Yes, it was an analog computer. One other machine they had was essentially to calculate the Fourier transform of a realization.
Right.
In other words, there is a theory of stochastic processes. Much more special case of this is time series, because it's much more elementary. You're not looking at distributions, you're on the whole looking at first and second order moments. And I did write down there for a moment an autoregression and a moving average. You're interested in one thing, in the covariance, the covariance between over a separation, xt and xt minus s. You're interested in that. You're also interested in the breakup into what's the word?
Into frequencies, or
yes, to break it up into frequencies. To see it as a sum of
trigonometric functions.
Trigonometric functions, or trigonometric functions, oscillatory functions, I would say. Oscillatory functions, see that. Well, first of all, we had this machine which in fact evaluated the periodogram. The way it worked was it was in fact built by the Navy. It was a huge thing. I guess they had their own reasons for it. They wanted to do Fourier analysis of signals and that kind of thing. So it was a big flywheel about 3 feet in diameter. And if you had a series, you wrote it out on a tape as a stripe of varying width. And well, this was stuck on the flywheel around, and the wheel was driven by an electric motor. You could set the speed of it, and you had it was illuminated at one point. From the illumination, you get a reflected signal into a photoelectric cell.
Ah.
And what this gave you, if you at a given speed, if you're getting this at a given speed, you'd be getting an indication of the strength in a particular part of the spectrum. It would actually tell you how much, yes, to what degree that was so.
Fascinating analog machine then to do it.
It was an analog machine. They did it. And if you put it up to a great speed and let it run down by itself, then you gradually get the whole periodogram. First of all, as it went at great speed, you get first the high frequency elements, and that would come down, and you get the whole thing. And that's exactly what it did. That was quite important. It led actually to another development. You're talking about getting the frequency spectrum of a series or something like that. And it's not really quite clear on how this is done. A series really goes from minus infinity to plus infinity as far as time's concerned. Well, you're not going to do much about between minus infinity and plus infinity. And the other thing is that they'll just give you a chop, a series over a given period of time. But what do you mean by the Fourier analysis of that? Because it's not the original series. It's distorted by being truncated. But a way around that is, you know, if you've got the thing on an interval on a time interval, instead of routing it around and joining it up, so that instead of talking about translation invariance stochastically on the whole line, you're talking about invariance under rotation around a circle, which is a much neater notion altogether. And what it indicates, in fact, is it has an interesting effect. If you have a signal running around the circle, which is invariant under rotation around the circle, it really has to be made up of, well, a single sinusoid would have to be, you don't want it sort of coming to the end and not matching. If it's going to match, that has got to be, well, the number of oscillations must be integral.
Right, the phase has to match as it
comes
back.
Yes, there's going to be, it must be. It means essentially that the frequencies which can occur must be some constant times a natural number. Mm-hmm. The natural number being the number of individual swings that one gets out of as you go around the loop. And so you get a kind of quantization in frequency because of that. The frequencies are restricted to natural numbers times some constant. Right. And so that's a kind of interesting fact in itself.
So Peter, the flywheel was where? It was back in New Zealand at the...
Yes, it existed in more than one country.
But you saw it at the New Zealand Department of
Science? We certainly
Science.
had one in New Zealand. It was very impressive. This thing sort of came up to speed. It was rumbling and got a high speed, and it was like a train going by. And then they let it come down. It would come down gradually. That was quite impressive. Yes.
That must have inspired some of your later work on time series, then.
Yes, I think it must have done. I mean, there are many electronic ways of getting a frequency spectrum. They didn't use electronic ways, they used this big flywheel.
The flywheel gradually slowing down to give you the range.
Yes, yes.
But you were interested in time series earlier than that, and this was yet just another example of a method of analysis.
It was applied. A thing I will be able to give you in a moment is an interesting version of time series in oceanography. Uh-huh. It was an Englishman who came out to New Zealand, and he introduced something quite novel on this. He actually could locate storms.
Right.
You know,
right.
just from analysis of these lines of detectors. Could locate storms.
It's quite striking, isn't it, to solve the inverse problem of where the storm was?
It's solving an inverse problem in some way or another.
Yes.
It's all very ingenious.
Yeah.
It's all very ingenious.
Uh-huh. So, Peter, I understand Maurice Bartlett was a significant influence on your early intellectual development. So, did you meet him, or did you just read his papers?
I had met him at that time. I read his works and the books and his papers, and he was so very convincing. I got to know, principally, I think, one of the articles he wrote a big symposium article. It must have been in the mid-40s or something like that. And that was something one read again and again. It had lots of seminal notions in it. No, I didn't get to know him until I came to Britain. Well, actually, when I was in Sweden, he came to Sweden too. he came to the station, and here was this man. He was damp, and he was a very pleasant person. He was always a very decent kind of a chap, and I respected him greatly. I think that I didn't expect. When we moved to Britain, I came to know him, and in the end came to replace him. I followed him in the chair at Manchester. It was on account of his support that I think that happened. And likewise, when I moved to Cambridge, I think his support, and again, counted for a great deal. But he was a very kind man, and he certainly was on top of the heap.
So in his work, he brought probability and statistics and mathematical structure to bear on various problems of...
Yes, he did. He considered real-life things. He had a feeling for physical problems. He certainly had an intuition, and this showed up. Right. Yes. Mm.
So the decision to go to Sweden for your doctoral work, what influenced you in that choice?
A great mixture of things. First of all, the Swedes were very clever. They'd done a lot of work on time series and things like that, in connection with all kind of things. In connection with telephone work, so you've got these big telephone companies, they have technical problems there. Forestry, in forestry you had all kinds of things that turned up. And the Swedes, they were technically very strong on these things, and so it was good to go there, and there was a high degree of scholarliness. The other thing, of course, was that, they were very athletic as well. I mean, the very good runners in those days were Swedish and Finns. And I mean, in the 1936 Olympic Games, 10,000 meters was Ilmari Kalminen. That was the Ilmari Salminen. He was the 10,000 meter runner. He won that. 5,000 meters. Volmari Isoholo, Finn. He won the 5,000 meters. 1,500 metres was a New Zealander.
You yourself were a cross-country runner.
Oh, yes, very much. No, not of national standard, club standard. But I did enjoy that. It was good. We got around a lot. That was very helpful. I enjoyed that. Same thing when I went to Sweden. In the morning, they had sessions in the gym, so to speak, and you sort of did a bit of free running round and about, and a few exercises, and then dip in the bath, and that was great fun. Right. Yes.
So at Uppsala, your supervisor was Herman Wald.
Well, Herman Wald, yes.
And so tell us about your time as a doctoral student.
Yeah, Wald was very helpful. He was nice. He was not of. He aimed to be one of the real quality scientists, or scholar, a real scholar. Which he wasn't really. I mean, compared with Cremier, for example. Cremier struck one immediately by his quality both as a man and his quality as a scientist. Wald was very good. He wasn't brilliant, but he was very kind. The thing I liked, I got along very well with the Swedes. The Swedes were very nice.
For a New Zealand boy at the other end of the world, everything must have seemed strange. The food, the climate,
Yes. Well, living in Uppsala, as I said, Wald was very kind and helpful to me. Living in Uppsala was pleasant. One could take these runs in the forest. Everybody was running in a sense. But it was student life. If I go back to student life, I could read a bit, actually, that I've got. Mm-hmm. A very happy social element in student life was provided by the nationerna, the nations. These were student bodies, each one taking as members all who came from a particular region of Sweden, roughly speaking, the counties. Their purpose was a very relevant one in the days when communications were poor and Sweden had a simple rural economy. It was to ensure that students far from home would have the practical and psychological support of the familiar, and so provide a social net, a safety net in time of trouble. Each nation had its own nation's house, usually a substantial and elegant building which offered all the amenities from an evocation of history to lively social life. For people like myself who came from outside, allocation was usually on the random grounds of social contact, personal contact. I've forgotten how it came about, but I was accepted by Westernemans Dalarna as one of the groups, and a very happy adoption it turned out to be. I came as a stranger, from overseas, and this was really post-war. The Swedes were generally very receptive, very hospitable, but one group they found difficult to deal with after the war was what they called the flyktingar, that means refugees. These were people who usually they'd had a tough time and they were carrying various medical conditions. And that's why if you came to the university, you had to go through a physical check. And I had a fairly anomalous result in that I had no disease at all. But that was the thing they were looking out for. I was perfectly healthy. But speaking of the social life in Sweden, I was still desperately homesick. And Värdala, the nation's house, offered alleviation from the lonely bedroom. There were feasts of one kind and another, with much singing. There were old-time dance sessions with wonderful Strauss waltzes and vigorous Swedish country dances. One they called Hambo, there's polka, schottisch, that's Scottish dancing. And there were weekend excursions to the country. There'd be long discussions in various friends' rooms in the evenings. The girls were bright and healthy, would have been very kindly, but I was already committed in New Zealand. In fact, by the end of my first term, I realized that social life was prejudicing my work. It was a deadline for me that I should complete my thesis within 2 years. I therefore cut back radically on attendance at Värdala, which really was a shame. It had provided the kind of free, lyric companionate experience that only the brief student years in such an environment can offer. The Swedes were, in general, very warm and hospitable. That was certainly the case. There's one interesting, it wasn't a counterexample, but it was a sort of halfway to a counterexample. There was a staff member, his name was Gunnar Eklund. He had a rather grating, abrupt, dismissive style of speaking. There was a time when I had been away from Uppsala for quite a period, quite long. And when I came back and met him, he gripped me by the hand, addressing me as gamle vän, meaning old friend. And in fact, I could see that his eyes were moist, which was surprising. I think this reflected simply friendship, warmth, idealism, which was certainly present in this particular case. Yes, this is an autoregression. Autoregression meaning regressing on itself. It is a difference equation of a certain order. You don't have to labour to produce a forecast. You just apply this repeatedly and it will develop a forecast, although somewhat random, of course, because of this. The other one is what's called a moving average. It's an average, well, it's not really an average, but it's a linear function of the disturbances which are coming in, the random disturbances which are coming in, which drive xt. As I said, we call it a moving average. The Swedes call it a löpande medelvärde, which really means a running average. In Sweden, when you go for your doctorate, you have to defend yourself. In other words, more or less as we're doing now, you have to stand and explain what you've been doing and answer questions on it, etc., etc. And the funny thing about it is that they regard this as a kind of a joke. The person who's doing the questioning is called opponent, and you have a first opponent, someone who and an under opponent, and Well, my opponent was making great business of this. He knew that I did a certain amount of running, and he says, here we have a löpende medelvärde, a running average. And well, it wasn't a very good joke, but they nevertheless tended to make jokes and well, look for
lighten the atmosphere.
Lighten the atmosphere up, yes. Well, the opponent really, there were two kinds. There were people who were really testing you, and that was part of the examination. And there were others who were really making a sort of circus performance of it, and for the general enjoyment. And you know, it was really a question of making a good joke rather than of making any great point. Right. So that was something. And they said that I had brought in löpende because I'd been running, etc., etc. They wanted to know where the running was.
Right.
Yes.
So these equations then were on your board for your thesis defence then?
Well, there would be similar equations, yes, yes. I forgot.
And then went forward into what became your first book on prediction and regulation.
Yes, that's true. That's true. It's a thing I've thought about is that it was the use of this machine in New Zealand, the big wheel turning about, which made me think of the development of the process the way it has. I mean, we were saying that instead of regarding the process as being on a stretch of time, it's really on a loop of time. And putting it on a loop has this quantizing effect. And that is interesting, that this notion of a loop, it occurs naturally in the machine, and it makes good mathematical sense as well. Mm-hmm. Yes.
Peter, thank you so much for coming along to be interviewed today. I'm so pleased you were able to do it. Thank you.
Well, thank you. I'm glad that you made me think about memories which are interesting, varied, and at their best, marvelous. Thank you.